This talk is about ozone depletion versus the ozone hole. In previous talks we talked about the equilibrium that exists between oxygen, ozone and oxygen free radicals in the stratosphere in what we call as the ozone layer, and there's a series of 4 reactions that keeps the concentrations of ozone, oxygen and oxygen free radicals fairly constant in the ozone layer. And we know that those 2 processes absorb UV light because the 2 decomposition processes there absorb UV as they occur. We also learned in a previous talk that CFCs, such as this chemical here, chlorotrifluoromethane, have affected the ozone layer because they produce these chemicals called chlorine-free radicals. When these chemicals reach the stratosphere where there is high concentrations of UV light, they decompose, producing the chlorine-free radicals. And those chlorine-free radicals are a catalyst for ozone decomposition, as shown in the reactions down here, because they react with ozone to produce this chemical here called chlorine monoxide. And that chlorine monoxide then reacts with oxygen-free radicals to reproduce the chlorine-free radicals, which then can go ahead and decompose more and more and more ozone molecules. And so chlorine-free radicals are effectively a catalyst for ozone decomposition. If we just look at that in a bit more detail, we can see how it relates to that equilibrium process taking place. If we look at those 2 reactions where chlorine-free radicals are decomposing the ozone, if we put those 2 reactions together, we'd see that some species appear on both sides of the equation, and therefore we can just ignore them for the moment. So we look at chlorine monoxide appears on both sides, and the chlorine-free radicals appears on both sides. So what we're left with is a process where ozone and oxygen-free radicals turn into 2 oxygen molecules, and that is one of the processes occurring in the equilibrium in the ozone layer. That's exactly the same process there. So what these chlorine-free radicals are doing are actually catalyzing this process. And initially, or naturally, these 4 reactions here were all in an equilibrium, which means their concentration stayed constant. But because the chlorine-free radicals catalyze this reaction, that means that process occurs faster than normal, which means the net concentration of ozone in the ozone layer decreases. And that's what we call ozone depletion. The fact that globally, chlorine-free radicals produced by the CFCs are destroying the ozone layer globally. There's a general reduction in the thickness of the ozone layer across the whole globe. That's ozone depletion. But something we hear about a lot is something called the ozone hole. And the ozone hole is actually a unique feature to the Antarctic, although they've recently discovered one in the Arctic, but it's a unique feature to the poles that only occurs in spring. And we're going to learn today about how that occurs, why their ozone hole appears during spring. And actually it links down to these 2 reactions down here. In the previous talk, we talked about how these 2 reactions actually stop the chlorine-free radicals from catalyzing ozone decomposition, because by reacting with nitrogen dioxide and reacting with methane in the atmosphere, the chlorine monoxide and chlorine-free radicals actually turn into chemicals that don't decompose ozone, and therefore the chain reaction where they catalyze ozone decomposition stops. And those 2 chemicals we learnt were chlorine nitrate and hydrogen chloride. And those 2 chemicals are storing chlorine, but they're not having any effect on the ozone layer. However, they do have an impact on the ozone hole, and that's because there's a certain atmospheric condition in the stratosphere. It's called the polar vortex. So in winter, in the Antarctic, there's some very specific features. Because it's winter and it's at the poles, it's very dark. It's very cold. And this thing called the polar vortex, it's a certain wind pattern, which means the air in the stratosphere is not mixing with warmer air from the troposphere. And that means it gets very cold and special ice crystals form. And what these ice crystals do is they catalyze a reaction between the chlorine nitrate and the hydrogen chloride. And that reaction is hydrogen chloride plus chlorine nitrate turns into normal chlorine gas and hydrogen nitrate. Now these ice crystals, from what I understand, aren't normal frozen water, but they are a frozen water sort of chemical. There's other chemicals involved too, but these chemicals catalyze the reaction of these two chemicals, hydrogen chloride and chlorine nitrate, to produce normal chlorine gas. And the important thing to know is chlorine gas itself has no effect on the ozone layer. So for the time being in the Antarctic winter, this chlorine gas builds up. So these little pictures on the side here, this is a representation of the Earth, in case you didn't realise that, and that white patch down the bottom is supposed to represent Antarctica. And so what happens in winter, we get basically accumulation of chlorine gas. But don't forget, it's very dark and very cold, and that chlorine gas is quite stable. The problem comes in spring, because in spring we have the return of light, but also that means the return of ultraviolet radiation. And that ultraviolet radiation can decompose these chlorine molecules. And what happens is this huge stockpile of chlorine molecules encounters UV light, and breaks down into two chlorine-free radicals. And as we know, chlorine-free radicals are catalysts for ozone decomposition. And so very rapidly we have a rapid decomposition of ozone all at once in the spring, which leads to the ozone layer hole. But that ozone layer hole is restricted to the Antarctic, where that chlorine gas was accumulated. So how do we draw an ozone layer hole? I've got no idea. Let's try. So there represents an absence of ozone above Antarctica at that point in time, because of the huge amounts of chlorine-free radicals in the atmosphere as soon as the sunlight returns in spring. Now by summer, the concentration of these chlorine-free radicals drops, because by summer these two reactions have taken place and have taken away the chlorine-free radicals. And also in summer we have mixing of air, because the thermal energy from the sun means the air is more likely to mix and the polar vortex breaks up. So no polar vortex. And that remixing of air means that ozone from the rest of the atmosphere is free to mix around the Antarctic, and therefore the hole closes in summer. However, the very fact that there was an ozone hole means there was rapid ozone depletion in the southern hemisphere then, and when the air mixes, that means there's a gradual thinning of the ozone layer in higher latitudes as well. And that means that thinning of the ozone layer can actually reach up as high as Victoria during that process, whereby the air is remixing again. So you can get quite large depletions of ozone cover on the southern half of Australia as the air is being remixed. And that's potential for big problems in Australia as far as skin cancer is concerned, because ultraviolet light, obviously as we know, can cause skin cancer. So that's a summary of how, first of all, the equilibrium in the stratosphere keeps the concentration of ozone fairly constant. Unfortunately, human actions in the production of CFCs have led to the production of chlorine-free radicals, which catalyze ozone decomposition. We learnt that catalysis of ozone decomposition is halted by two reactions, but the products of those two reactions in the Antarctic winter can lead to the production of chlorine gas. Chlorine gas itself has no harm on the ozone layer, but in spring, when the light returns to the Antarctic, that chlorine gas decomposes back into chlorine-free radicals, which starts the whole process of ozone decomposition again. In summer, the chlorine-free radicals have been consumed again, because once again of these two reactions consuming the chlorine-free radicals, and also the air starts to mix again because of the thermal energy in the atmosphere, which means the ozone hole closes, but there is a global depletion of ozone again.